Thanks to our work in Module 3a, we now have a robust method of generating an arbitrary order solution approximation. But in comparison to the simple linear solver that we developed in Module 2, it's impractical to assume that we can pre-calculate all the integrals analytically, because we may have any particular arbitrary order solution approximation. So we need to use some sort of numerical integration technique, commonly called quadrature, which you've likely seen in some of the assumed prerequisite knowledge. So rather than trying to analytically integrate our functions we know ahead of time, we're able to numerically integrate arbitrary functions. So this operates on the fact that if we can find an interpolation of a function that is sufficiently accurate, then we can assume that we can use that interpolation of the function anywhere we could use the function itself. So in general, this would be m-1 order accurate, where m is the total number of points in the interpolation. So here we can see we're making this substitution, and we're using a Lagrange basis for our interpolation. So if we substitute this in for an integral, we can see that we can separate out the terms that don't depend upon the region of integration. So we just simply have ultimately the integral of our Lagrange basis. And it turns out that if the nodes of your Lagrange interpolation are Legendre roots, then this integral is just simply the associated quadrature weight with that quadrature node from the Legendre roots that you would get from a Gauss-Legendre quadrature. So in reality, we can do a little bit better than, or actually quite a bit better than, the m-1 order accuracy for the quadrature. So recall that an Hermite interpolation builds upon Lagrange interpolation by not just using the value of the solution at a set of nodes, but also some subset of its derivatives at those points as well. So consider an Hermite interpolation that has first derivatives at the nodes in addition to the value of the function itself. So because we have 2m pieces of data, we get a 2m-1 accurate interpolation. If we then in turn attempt to generate a quadrature from this, so in other words, integrate our interpolation, then we find it takes on the form of essentially the underlying Gauss-Legendre quadrature plus some extra stuff that handles the interpolation from the being able to use the first derivatives of our function. It turns out, though, if we choose our quadrature points to be the Legendre roots, this integral right here is 0. So what this means is, even though we may specify our derivative of our function at our quadrature points, it doesn't matter because ultimately they're 0. So we're able to retain a 2m-1 order accurate method without ever actually needing to specify the other m points. All we need is the value of the function itself at m points, and we're able to recover a 2m-1 order accurate quadrature. It's important to note that this trick works for the quadrature, but it doesn't work for the interpolation. In order to get a 2m-1 order accurate interpolation, you would still need the derivative of your function you're interpolating at those points. It's only by virtue of the integration for the quadrature do we gain the ability to ignore those derivatives.